Hello, we are the Spacecraft Data Wrangler team from Purdue University, a part of the data mine and the Aerospace Corporation partnership. Our project deals with an unseen technology which has far-ranging implications in all of our lives. Above our heads, thousands of satellites are in orbit. They are constantly receiving and transmitting huge amounts of data. Countless groups across government, industry, and everyday life depend on this data, but analyzing and interpreting all of it is a huge challenge.
This project attempts to address a major aspect of this problem, the identification and analysis of anomalies caused by interference originating from a variety of sources. By doing so, we aim to help minimize the impact of interference and draw important insights from anomalous behavior. Furthermore, we hope to make the process more streamlined and efficient.
The technology we're dealing with is broadly referred to as a Global Navigation Satellite System, or GNSS. GPS is one type of GNSS. Some important data fields which we've worked with are signal-to-noise ratio, or SNR, and pseudo-range. Broadly speaking, these variables help us to determine where a satellite is and how confident we can be about that information. Several factors can interfere with the data. They include space weather, equipment artifacts, and manufactured interference.
By analyzing anomalies, we can glean important information regarding these interference sources. On this project, we deal specifically with data from the GRACE mission, which produced Rhinex telemetry data. There are many other formats, but we began with Rhinex to keep the project scope manageable. The GRACE mission was selected because it provides a wide range of data fields which are common across the industry.
Now we'll talk about the processes behind identifying these anomalies. One method we use is applying geospatial analysis, where we plot SNR over geographic regions and search for patterns. This helps us to determine whether there are patterns in the fidelity of data with respect to where a satellite is over Earth.
Another method to identify SNR anomalies is to examine recurring passes between GRACE and the GNSS constellation. We can also conduct pseudo-range analysis, where we compare the predicted location of a satellite versus where the data is telling us that satellite is. This involves the use of an important process known as estimation filtering. This is where we combine our expectations for the system with the noisy data we've received and make a more informed best guess as to the true state of a system.
This allows us to place error bounds on our data, which is critical for determining whether a measurement is truly anomalous or within expected bounds. By combining SNR and pseudo-range analysis, we can see how these variables behave in relation to each other and in relation to the distances between different satellites.
We combine these processes into a web application. The goal of this app is to facilitate a one-stop-shop data pipeline that allows the user to upload and unparse Rhinex data file, parse the file, search for anomalies, and display visualization based on the data. This app's purpose is to streamline the workflow of satellite telemetry at the Aerospace Corporation. As it stands currently, this process is time-consuming and demands expert-level knowledge.
Thanks so much for listening to our presentation.